So if you recall, we've been talking about different variants of the Java Executor framework. We talked about the Executor, which was kind of limited. We talked about the Executor Service, which had a lot more features. We talked about the Java Executor Completion Service. And then that leaves the last piece in our puzzle, which is the Java ScheduledExecutorService. And what we'll do here is kind of talk about what this provides and some of the related classes and interfaces that are used with the ScheduledExecutorService. So the ScheduledExecutorService extends Executor Service, so it has all the Executor Service stuff. And it's used to schedule commands that will be run after a given delay, or it allows them also to be executed periodically. It's a fairly simple interface, although the implementation is clever and tricky, but the actual methods are pretty small. The Scheduled Executor Service is implemented by the Scheduled Thread Pool Executor class. And so this shows all the different pieces involved here. So we have the Scheduled Executor Service, which, as you can see, just has a few methods that really are interesting for our discussion. But then there's this thing called the Scheduled Thread Pool Executor, which has all kinds of other stuff in it. And this implements Thread Pool Executor. And it also goes ahead and has this thing called a Scheduled Future task in it, which is used to run things. And it also has something called a Delayed Work Queue. Some of these things are implementation details we won't go into much discussion of. They're just part of how it is implemented internally in order to be able to do the features we're going to focus on. OK, so there's 4 main methods in the Scheduled Executor Service interface. All of these methods accept relative delays. That means relative to the current point in time when you call them. And so it doesn't take absolute times. Here are the 4 methods. 2 of the methods are used to create tasks with various delays. You can see here we have schedule, which takes a callable, and we have schedule that takes a runnable. So this basically lets you do 2-way calls. This lets you do 1-way calls. And what this returns is basically something called a scheduled future. So a scheduled future is a future and a delayed, and so it's going to have the ability to do all the future operations as well as find out how long it'll take before the thing gets run. And I'll show you an example here in a minute of using a scheduled future. There's also a pair of methods that are used to create and execute tasks that will keep running until they're canceled. And so you can run, there's one called schedule at fixed rate, which will run a thing. It'll give an initial delay, and then it'll run it at that point. And then there's also something called schedule at fixed delay. And again, these methods return an object that can be used to cancel or check the execution status. Sometimes you need some clever design techniques in order to cancel the runnable command. And I'll show you an example of this when we talk about the TimedMemoizer, which is a super cool extension to the Memoizer class that we had talked about last time. All right, so that's the end of that particular part of the lesson. So now that we've talked about the Scheduled Executor Service interface, let's give an example of how it works. And what we'll do here, of course, is take our PrimeChecker app and enhance it to use the Scheduled Executor Service interface. So I'll just reiterate this briefly. So we have the PrimeChecker app, which is embarrassingly parallel. This is the new version that you can use that'll showcase the Scheduled Executor Service and how it works. As before, we have a pool of threads, we have as many threads as there are cores on the machine. Similar to before, we have a prime callable that has a PrimeChecker function in it, and we basically delegate the call to the PrimeChecker function, and that way you can parameterize what kind of PrimeChecker you want to have in here. Same issue with PrimeResult, just gets the results back. Here's where things get a little bit different. This time we have a PrimeMemoizer. This should say TimedMemoizer, not Memoizer. I originally called it Memoizer, but that was confusing, so now it's called TimedMemoizer. And you can give it a count here, and the count is basically the number of milliseconds before an item is considered to be stale in the cache, and you'll see how that gets used in a second. Otherwise, this thing is basically the same as it was before. We have a stream, and the stream goes ahead and makes random numbers, and we go ahead and turn those into prime callables, passing in the PrimeMemoizer, and then that's submitted to the executor service, and it runs. And you'll see how the timeouts work in a second. Philip.
I just have a question on when you asked me to put in the available processors, is it getting those from the virtual machine or the actual machine?
So the virtual machine knows how many cores are on the platform. So that's one of the things that the virtual machine implementation would know is how many cores there were. And so that's going to return that for you. And on most machines these days have multi-core, and they're true multi-core. There was a period of time when people had what were called hyper-threaded processors, and those are also counted as cores, although they don't behave quite the same as a true core would. But nowadays, most chips have true cores. All right, this is the same as before. We make ourselves a completion runnable. We run it in a separate thread, and that just waits for the results to finish. And nothing really new here. We use the take method to get the next available completed future, and we work with that. The retained state, same as before as well. It just keeps track of all the things you want to live between rotations when the phone is turned, and so on and so forth. OK, so let's now go ahead and talk about the PrimeChecker app, and I'll run it for you later. So the main thing it does is it fixes a problem we had with the Executor Completion Service version, the one we looked at last time. And what it does, basically, is it has this thing called a TimedMemoizer. And the TimedMemoizer has some real cool logic in it using a ScheduledExecutor service in order to purge the items in the cache when they become stale. And I'll talk about what stale means in a second. But the main thing that we're doing here is we're not letting the cache just fill up indefinitely. We're letting the cache fill up. And as long as something is accessed within the last time period, then it sticks around. So what we're doing is we're basically saying, as long as items in the cache are accessed periodically, then they stay around in the cache. If they're not accessed periodically, they get purged. Now, that's, again, not a perfect solution, but it's one way of being able to make sure things don't grow indefinitely, which is really the goal of all this. All right, so let's kind of see how we're going to do this. So the TimedMemoizer we have now, the new one, is going to use concurrent hash map like we did before, a future task like we did before, and a ScheduledExecutor service. This is the new part. And we're going to use this to limit the amount of time that a key and a value remain in the cache before they're thrown out. And we'll see that there's a couple different implementations I'll show you how to do. To make things much more readable and to make it easier to demonstrate the different implementation variants, I have a bunch of private methods that are used to kind of break the logic up. I also defined something called a ref-counted future task, which is a super cool little trick I have here in order to be able to do the reference counting so I can tell if something has been accessed recently, where recently is between within the last period using the timer mechanism. So you can figure out how many times a key is referenced within a given number of milliseconds, and you'll see how that works. All right, so let's take a look at this. Here is ref-counted future task. So ref-counted future task is a future task. If you recall, what did we use the future task for in our original implementation? Why did we have a future task? You remember why? There was a specific reason why we used future task. So the reason for using future... No. The reason we used future task was to make sure that there was never more than one computation of the function, even if multiple threads showed up at the same time when there was nothing in the cache. So future task was a real important element in our original solution. And now what we're going to do is we're going to extend it, so we're still going to use it for that same purpose, but we're also going to add a ref count that keeps track of the number of times a key is referenced. And so you'll see why we need to do this and why we have to make it atomic so it can be accessed from multiple threads. The constructor simply makes a new atomic long and passes the initial count into the atomic long, and it also calls up to the future task, passing in the callable. We are now going to override the equals method, and you'll see why we need to do that when we get a little further along. What the equals method is going to do is first it's going to make sure that we're indeed both elements are from the class. They're both ref-counted future tasks. That's the first thing we do, and we do that by comparing whether the classes are equal. That's just a typical way to implement equals. And then we go ahead and we cast the object to a ref-counted future task, and we compare the reference counts. And if the reference counts are equal, then these two things are equal. If they're not equal, then it tells us something else that we'll talk about in a second. And then the final method that we have here is we override the get method. Remember, get method on a future task will block until the future is completed, until the result has been triggered. And we do that here. We block until the value is computed, but then we also increment the ref count by 1 and return the value. And that's just to kind of clean up the code down below, so it's a little bit easier to read. All right, so that's what a ref counted future task is. And so we're using it for two purposes. We're using it to make sure there's only one call to the function, and we're also making it easy to atomically keep track of how many times something is accessed during the period of time we're trying to keep track of. OK, here's the Memoizer. This should be TimedMemoizer. I've got to fix this in my slides. So TimedMemoizer. And we start out with a method called apply. So you can see apply is a lot shorter now. So apply goes ahead and looks up in the cache to see whether or not we have the key. And if there is a key under that name in the cache, we get back the ref counted future task, in which case future will not be null. And if future is null, we compute the value that's associated with the key. And we'll look at that implementation in a second. By the time we get done with this piece of code, either we got back the cached value or we've computed the new value. And then we go ahead and get the future value for the key in the future. And you'll see what that does in a second. That basically just does the logic that waits for the result to be done, if it's not already done. OK, here is compute value. So this is the thing that's going to get called if this is the first time in. So you can see what we do is we create a ref counted future task. We pass it a lambda expression, which will go ahead and actually do the call, which will apply the function. And we pass it a 0. And I'll talk about why we pass it a 0 later. Once this thing is created, then we try to put this in the cache as the value of the key. Remember, put if absent is this atomic check, which will atomically add something into the concurrent hash map if and only if it's not already there. So if it's not there, it'll atomically add it. If it is there, it'll return what was there before. So we can find out whether or not this is the first time in by checking the return value. So if this comes back with null, then we've got some work to do because we have to compute the function. If it comes back non-null, that means that the future task is already in the cache. Now, it may not be computed yet, but it is in the cache. And we'll see how that gets used in a second. Let's look at the more interesting case. This is the case where the value has not been put in the cache, in which case we run the future task in the thread of control of the caller, and that'll block until the value is computed. In the case of the prime number application, it'll run the prime number call. And then what we're going to do is we're going to schedule a timeout. You'll see how that gets used in a second. And we return the future task. So that's what compute value looks like. Let's take a look at scheduled timeout. There's going to be two different implementations. This first one is the simpler one. And it demonstrates one set of pieces of the scheduled executor service. And the next one's a little bit more interesting, and it shows another piece. So what we do here is we only schedule timeouts under the right conditions. So if the thread has been interrupted or the timeout in milliseconds parameter is 0, or there's no need to schedule a timeout because either we've been told to shut down or we were not told to do the timeout mechanism. In this case, we go ahead and we create a ref counted future task called non-accessed value. And notice that has a count of 1. So as we'll see later, anytime a value has a count of 1, that means it hasn't been accessed over the period of time that the thing has been, over the period of time that we're using to be the period where we're checking to see if anything happens in that time frame. So if a count of 1 simply means nobody came along and incremented it in that time frame. So that'll get used as a flag, an important flag, and we'll see in a second. We then go ahead and we create a runnable called remove if stale. So this is going to be a new runnable that's going to have a run method. And I'll show you what the run method does in a second. It turns out to be important that this be a runnable, not a lambda expression. And I'll explain that in a second as well. So here's the implementation. This part here is just the continuation of this run method in the runnable. So what we do is we come along and we try to remove the key from the cache with the non-accessed value. So what the heck is going on there? There's two different remove methods on a concurrent hash map. One remove method on a concurrent hash map doesn't take a second parameter. So it just unilaterally removes the value associated with the key, and it removes the key as well, right? So that's just the unilateral remove. It removes it unconditionally. The second remove is a more interesting remove. It removes a key if the value that's stored in the concurrent hash map matches the parameter that's passed in as the second parameter to remove. So what we're doing here is we're passing in non-accessed value. Non-accessed value, if you recall, had a reference count of 1. And so what we're saying here is, we're saying if the key has a value with a reference count of 1, we're actually going to remove it. And the reason for that is that that means it wasn't accessed since the last time. If it's not 1, it means somebody came along in that time frame and accessed the count, accessed that key, and it incremented the count, as we'll see here in a second. So what we're going to do here is we're going to assume the case where this has been accessed. So it's not a value of 1. So it has been accessed. So if something has been accessed, what we're going to do is we're going to come in and we're going to replace the value of this key with the non-accessed value. So we're kind of resetting it again. And then we're going to schedule this runnable, which is this guy. We're going to schedule remove if stale for another period. So it'll be called back in another m timeout in milliseconds period. So what we're doing is we're scheduling this thing, and every time it runs, it checks to see if anything happened since the last time it was run. If nothing happened, that meant nobody accessed it, so it's stale, so we remove it. If it has been accessed, then we go ahead and reschedule it to run again in the next chunk of time. So that's what this clever little runnable does. And then, irrespective of what the runnable does, the first time in, we schedule remove if stale to run in m timeout in milliseconds. So that'll then run the first time. So you can see we're basically setting this up kind of like a bucket brigade or something, where it schedules it for the first period. When the timer goes off, it'll come back and it'll come back again, and then it'll go ahead and check to see whether or not it's been changed. And if it has been changed, it'll reschedule again to come back in that period of time and try one more time. Ann?
Can you go back to the equality operator?
Yes. Great point. So this call here, remove, right? This call is going to check to see if the value equals this value. And so that begs the question, what's that check? And here's the check. So equals on a ref counted future task, which is what gets stored in the concurrent hash map, that is ultimately going to check to see what the ref count values are. So what we're saying here is if the current value in the hash map equals the not accessed value, which has a ref count of 1, then they're equals. So keeping that in mind, the remove, whoops, where did it go? The remove method will succeed in that case. So what that's saying is, putting it in English, it's saying, try to remove this thing if it hasn't changed over the last period of time. That's what that's doing. So this is really cool because this is atomic. That's an atomic check. And so you won't get into this code down here unless this atomically determines that it's got this value of 1. In other words, it hasn't been accessed. All right, so that's one implementation. Here's another implementation. This is a little bit more complicated, but it demonstrates some other things. So this is a schedule at fixed rate timeout implementation. And so what this does is this is going to do the following. Let me give you the high-level view. It's going to go ahead and it's going to schedule a cleanup runnable, and it'll schedule it to run at a fixed rate until it's canceled. So what's going to happen in this implementation is you're going to schedule this thing, and it's going to keep running. And every time it runs, it'll check to see if it was accessed in the last period of time. If it was not accessed in the last period of time, then the implementation will cancel that runnable. If it has been accessed in the last period of time, then nothing happens, and it'll just get called back automatically in the next period. Philip?
So what's the difference between the other destination that schedules it again.
Right. So that's exactly right. So the one we just looked at schedules it one time. It's a one-shot. This is a one-shot schedule, right? We're scheduling this one shot. And then every time the thing goes off, it does a few checks. And then if it needs to reschedule, it explicitly reschedules it. So this is what we might call explicit rescheduling. So this is one where you have to keep rescheduling it every time. The one we're about to look at schedules it to run indefinitely at a certain rate. And if it turns out that it doesn't need to keep in the cache, it'll explicitly cancel it. Right? So it's two different, it's sort of two sides of the same coin. Ann?
So it continues to reschedule the runnable
Automatically.
even though it doesn't, like, even if you remove,
Oh, if you remove it,
yeah, even if you remove it, do you keep checking?
no. You'll see. Obviously, if you remove it, then you cancel the timer. So the first one, you had to explicitly keep rescheduling it. This one, because of the fact we're using schedule at fixed rate, it just sticks around, and then you have to cancel it if you don't want it anymore. So it's really the inverse. Marion?
So is it scheduled per key?
Yes. Each key will have a timeout runnable that will check whether it's time to go. Yes, absolutely. That's right. All right, this one turns out to be trickier for some other reasons too. So take a look. The first part's the same. We check to see if we've been interrupted. We check to see what the millisecond relationships are, blah, blah, blah. We create a non-accessed value. That's all the same as we had before. But now we're going to have to do something new. We're going to have to create this new class called delegating runnable. And you'll see why we use the delegating runnable in just a second. A delegating runnable implements runnable, and then it stores a runnable. What the heck? And its run method, as you can see here, when this guy's run method gets called, it just turns around and it delegates to the runnable that it has as a parameter. And the reason we need this is because we have this mutual dependency here, and we have to make sure we can schedule a runnable and also be able to cancel it. And that requires some magic. And you'll get a better sense of why we need that on the next slide. OK, so here is the rest of this code. So schedule at fixed rate timeout does everything we just saw, ... Then it goes ahead and it creates a new delegating runnable. And then it goes ahead and it schedules this delegating runnable at a fixed rate. So it'll wait this amount of time, and then it'll keep calling back on the delegating runnable every one of these periods. It'll keep calling this back periodically at a fixed rate, and it'll call back on that run method. It'll keep calling back the run at that fixed rate, unless we cancel it. That's the magic. So what we then do is we go ahead and we set the runnable in the delegating runnable. So we're going to go ahead and set this actual runnable, see, actual runnable. The actual runnable is going to be set to a lambda expression, and that lambda expression will keep getting called back at this fixed rate with this initial millisecond delay. And every time this lambda gets called back, it's going to try to remove the item from the cache using the non-access value. So in other words, if this value has not been accessed in the period of time we were just discussing, in other words, its fixed period of time has not been accessed, then we're going to cancel it. And notice how we're going to cancel it. We're going to call back on the cancelable future to cancel this runnable from the scheduled executor service. So if it's its time to go, we cancel it. Otherwise, in other words, if it was accessed, then we go ahead and we reset the value to the non-access value so that it's kind of reset to being back to the initial state. And this thing will keep getting called back over and over and over and over and over again. So the reason why we had to have the delegating runnable was because we needed to be able to have a way of scheduling a runnable that would be able to access the future that came back from schedule at fixed rate. So schedule at fixed rate returns a future. We need that future in order to be able to stop this runnable from running. And it turns out you can't really do this any other convenient way to get the future in the right place. Now, another little funny thing to note, notice we could use a lambda expression here, but back over here, we were not able to use a lambda expression. So remove if stale had to be an actual anonymous inner class instance. So new runnable, run, and blah, blah, blah. This cannot be a lambda. And the reason this cannot be a lambda is because we needed to be able to schedule this object. And it turns out that lambda expressions are actually functions, not objects. And so as a result, they don't have a this, or they don't have the right this, they have the enclosing this. They don't create a new scope. A lambda function, lambda expression, does not create a new scope. And therefore, we had to actually make an anonymous inner class object in order to be able to schedule this thing to keep running over and over again. Very, very, very subtle point. It's actually something I didn't really understand in detail until I did this example with a friend of mine named Monty, and we realized that you had to create an anonymous inner class instance. All right, so the key point of all this is now you know two different ways of scheduling things. One where you schedule stuff for a one-shot timeout, and then when the timeout occurs, you check to see if you need to reschedule yourself. That was the first implementation. And then this second one is you schedule yourself, which will automatically get rescheduled every time you run, and then you have to cancel yourself when you don't want to keep running. Ann?
Why did we replace the non-access value? Or replace the value of the key?
Why do we replace it here?
Yeah.
Because that resets it so that for the next period, we can check to see if it's been updated.
But if we brought into the else block, doesn't that mean it's already 1?
No, if we try to remove it and it's not 1, if we try to remove it and it is 1, we cancel, right? If we try to remove it and it's not 1, we need to reset it so that it's back to its initial state for the next go-around, so we can see whether or not it's been updated, incremented.
So we not remove it?
We're not going to remove it. Well, this will remove it. So the way that remove works is if it turns out that this parameter, non-access value, is not equal to what's in the concurrent hash map, then it's not removed. If they're not equal, it only removes it if they're equal. So what this is saying is, remove this key if nothing's changed. And if nothing's changed, we have indeed removed it, and then we cancel the future. However, if we call remove and non-access value, which has the ref count of 1, doesn't equal the current ref count that's entered in the map for that key, let's say it's 2 or 3, that means that the key has been accessed since the last time we did this check, this timeout check. So if it's not equal, we don't remove it, and then we come down here and we replace the value that was 2 or 3, in other words, it's been accessed, with 1 that's back to 1 again. So we're resetting it so that the next time this gets called back, we can check to see if anything's changed. Yeah, it's pretty subtle. It's really, really cool, but it's subtle. All right, here is the final piece of the puzzle. This is the getFutureValue function. This goes ahead and calls future.get. And if you recall, future.get would block until the value is computed, just like a regular call on a future, and then it increments the reference count by 1. And so that's how we can tell whether or not something's changed since the last time the timeout check was done. So over here, this call here will block, and then it'll increment the ref count by 1. So every time this gets called, it'll get incremented by 1. So if it turns out that the ref counted future task, if the key, that's the way of getting to this ref counted future task, is accessed in that period of time that we told the TimedMemoizer is our period to check, then the ref count will get incremented by 1. And so as long as it's not 1, that means somebody touched it. And so the way our cache works is if something's referenced it, we assume it'll be referenced again. So it's a typical caching mechanism. If anything goes wrong, if there's any exceptions, then we remove there should be a semicolon here. We remove the key from the cache. And that's a unilateral remove. That just takes it out of the cache, doesn't care what its value is. So that just says, hey, if something went wrong, get this key out of here. We don't know what happened, but we don't want to keep the key around. The most typical thing that will have happened will have been that somebody will have interrupted the thread, in which case we want to clear this out. Okay, so that's basically the implementation. Any questions about that?